we'd like to talk about slope and how it relates to physics. And you'll see this come up, the slope come up quite a lot, because in one of the things that we talk about in physics is rates of change. And anytime we talk about the rate of change, that is a slope. And so you'll see this come up when we talk about position, and the rate of change of position is the velocity. You'll see it come up when we talk about velocity, and the rate of change is the acceleration. So you'll see it come up in kinematics. You'll see it come up in our discussion of potential energy, and you can see it come up in other topics as well as you advance through physics. You may have heard of slope being defined as the rise over the run, and that's a really useful mnemonic to remember. Of course, what this is the change in the vertical component over the change in the horizontal axis. Or in other words, this is y final minus y initial divided by x final minus x initial. So let's look at our three types of graphs that we have in physics. The first one is the constant graph. And as you might guess, it's constant, right? So our change in y is 0. It stays right here all the time. Well, then, if we looked at our slope, our slope is change in y over change in x. Change in y is 0. Change in x can be anything we want, as long as it's not 0. And we will get a slope equal to 0. So if our slope is 0, if our graph is constant, our slope is 0, and anything that depends on that slope will also be 0. Our linear graph ends up still being pretty simple. If we looked at our straight line graph, we can look at 2 points, right? Maybe this point right here and this one right here. And we can calculate the slope between those 2 points. We would say find where the first point is on the x-axis, find where the second point is on the x-axis, and that would allow us to calculate delta x. Then we would come over and we would find where the first point is on the y-axis, find where the second point is on the y-axis, and this would allow us to calculate delta y. And then the ratio of those two would be the slope. One interesting thing about this is this gives us the slope between any 2 points. If this were, say, the position versus time graph, then that would correspond to the average velocity between these 2 time points. But since it's a straight line, we know that we can pick any point on this graph, and it's going to have the same slope, the same tangent line. So if we drew a line through that point tangent to this blue line, it would exactly run along the blue line. And so for a straight line graph, for a linear relationship, then my average value is equal to my instantaneous value. So in this case, if we said if our slope was our average velocity, then that is also equal to my instantaneous velocity. Now this is only so long as this is a linear graph. The last graph is the most interesting, and that's the quadratic graph. We can look at 2 points, and we can use the slope to calculate the slope equation to calculate something between these 2 points. But what we will find we have done is we will have calculated the slope of a line that connects those 2 points, and it is this line. So that doesn't give us necessarily the slope at this first point or the slope at this second point, because we haven't really well defined what that is. Instead, it gives us sort of the average slope between those 2 points. What we can do, though, is we can think about it. We can make a thought experiment. What would happen if we brought this second point closer and closer to the first? Well, if I brought it, say, to here, I would make a new line that connects those 2 points. And if I kept doing this, I could bring it to here, and that would make a new line. And eventually I would get so close that I'm right on top of this first point. And I would get a line, and it's hard for me to draw that line, but I would get a line that is tangent to the curve of this graph. And that is then what we talk about when we talk about the slope at a point on a curve. It's really the slope of the tangent line that passes through that point. Now, this then gives us our instantaneous value. So if we have a quadratic graph, we have to do this moving the points closer and closer together to get our instantaneous value, or we have to look at some other method to get the instantaneous value. Now, to do this, that requires some advanced mathematics. And so we'll look at that, but if you're in a course that doesn't require calculus, then don't expect to have to know how to do this. Just understand that when we take the slope and we use the slope formula to calculate the slope between 2 points, we're not really taking the slope at a single point, we're taking the average between those 2 points. And we're getting this average line between them. If you're taking calculus concurrent with this course or have taken it previously, you may recognize that when I say slope, we're really talking about the derivative of a function. Now, what is the derivative of a function? Well, if I wanted to find the rate of change at this point, I could look at a point far away and find the slope of the line that passes between those 2 points. Now, as I make my second point closer and closer, that line would get closer and closer to being tangential to this first point. And right at the moment where those 2 points overlap, we would get then the line of the tangent through that point. And that is the rate of change of my function at this one specific instant. Mathematically, we said that our slope was equal to our change in y over our change in x. Or another way we could write this would be my y, the value of my function, at x plus some change in x, right? Some later time or later position or later whatever my x value is, minus y at that first initial x value divided by delta x. And then as I move these points closer together, I'm taking a limit as my change in x goes to 0. Get the points closer and closer together. And this is the definition of the derivative of my function with respect to x. So when we talk about slope, we can find instantaneous values of a curve by taking the derivative of our function. Now, your first calculus class will spend most of the course teaching you how to take derivatives. For this class, we will keep things simple. All I want you to know how to do is to be able to take the derivative of a polynomial. And when I say polynomial, what I mean is that if I had a function, it must have this form. That it will be some constant times my variable raised to some power. Now, there could be several terms in this polynomial, right? If I had a function that was, say, 2x squared plus 4x plus 1, that's still a polynomial, because if I looked at this, every term in this function has this polynomial form. The first term has 2, which is a constant, times x, which is my variable, raised to the power 2. The second term has 4, which is a constant, times x raised to the power 1. And the last term has 1, which is a constant, raised to the times my variable raised to the power 0, because anything raised to the 0 power is 1. To take the derivative of a polynomial function, what we're going to do is we're going to look at our exponent. And we're going to take that exponent, and we want to find the derivative of y with respect to our variable. We're going to take that exponent and multiply it down the front. Then we're going to take our function, we're going to write it out, and we're going to write our exponent, but we want to subtract 1 from that exponent. And that's the power rule. This is how we will find the derivative of a polynomial. This is called the power rule. And if I had multiple terms in my polynomial, I would apply this power rule to every term in the polynomial, and that would give me then my derivative of my function. Now suppose I wanted to find the value of my slope, so the value of my derivative at some time. So let's say this was x equals 3, and I wanted to know what was the value of the slope at x equals 3. Well, then I would use this power rule to find my derivative, and then in my result, everywhere I had my variable, I would stick in x equals 3. I would stick in the value 3, and that would give me then the slope of my tangent line at the x equals 3 point. So let's go through a quick example of how to take a derivative of a function. Suppose we have a velocity function, and the function of my velocity is 3t squared plus 2t plus 5, where 3, 5, and 2 have the appropriate units. What then is the derivative of my velocity with respect to time? So I want to know dv dt. We said if we want to know our derivative with respect to time, we have to use our power rule. So I'm going to look at this first term in my velocity function, and it has a form that is ax to the n. So I'm going to take n, and I'm going to multiply it in front. Then I'm going to take my function, I'm going to write it, 3t, but I want to write my exponent, and I want to reduce it by 1 power, or by 1 number. That's my first term. And I can keep going, right? I go on to the next term. I'm going to add up my terms. So my next term is 2t. So I'm going to write, this is 2t to the 1. So my power is 1. I bring it down. 2t to the 1. But then I want to subtract 1 off that power. And then I need to do my last term. This is 5t to the 0. So I'm going to bring down my power, that's 0, times 5, t to the 0 minus 1. Now, a mathematician may scream at the fact that I just wrote t to the 0 minus 1. A physicist, we just shrug and keep going. Now when I simplify this, right, now I can work out what my derivative is. 2 times 3 is 6t to the 2 minus 1, that's 1, so 6t. 1 times 2 is 2. T to the 1 minus 1, that's t to the 0, which is just 1, right? Because any number to the 0 equals 1. That's something you should keep in your mind. And then I have 5 times t to the 0 minus 1. So I'd have t to the minus 1 times 5 times 0. So everything gets multiplied by 0. This whole thing just goes to 0. And that's why we just sort of shrug and ignore the fact that we're being a bit slipshod in our math. So there is our derivative. It's just 6t plus 2. Now, what is this derivative? Well, it's velocity divided by time. We've already said in class we know that this is the acceleration, but let's just check if our units work out. We had velocity, which is meters per second, and we have dt on the bottom, which is seconds. You've seen this before. This is then meters per second times 1 over seconds. Those are equivalent. So sure enough, we get meters per second squared, and that is units of acceleration. So this is then the derivative of our velocity function. And if we wanted to find the acceleration at t equals 2 seconds, we could take our value and now plug it into our acceleration function, the derivative that we found, and we would get that our acceleration is equal to 6 times 2 plus 2, or in other words, this is 14 meters per second squared. And so if that was our function, our velocity has this function, then at 2 seconds, we would find that our acceleration is 14 meters per second squared. So hopefully that gives you an idea of how to deal with the concept of slope and how it might come up in physics. We'll get lots of practice using this, especially when we're talking about kinematics. And so don't stress out too much about it, but try to understand how to use the slope, how to calculate the slope. It will come up in the course.